Welcome to The Explainer. Today, we're digging into a new paper that could seriously shake up how we train our robots. We're talking about a shift from robots that just imitate us to robots that can actually learn from their own experience.
And at the heart of this paper called SimpleVLA-RL is this exact question. It's a direct challenge to the way we've been training our most advanced robots for years.
All right, so here's the game plan. We're going to start with the huge problem facing robotics right now, then introduce this paper's really clever solution. After that, we'll look at some jaw-dropping results, see if it actually works in the real world, and wrap up with what this all means for you as developers.
Okay, first things first. Let's set the stage. Modern robots, the really smart ones, use what are called Vision Language Action Models, or VLAs. It's how they see, understand, and act. But they have this one massive weakness.
See, most of these VLAs are trained using something called supervised fine-tuning, or SFT. It's basically just imitation learning. A human operator does a task, the robot watches and records, and then it tries to copy what it saw. This creates a giant data bottleneck, because getting thousands of high-quality human demos is incredibly expensive and slow. And worse, it creates robots that are good at copying, but pretty bad at generalizing to new situations. So the paper asks a really smart question. If reinforcement learning was the key to unlocking next-level reasoning in LLMs, with things like RLHF, couldn't that same idea solve the data problem in robotics and get us past simple imitation?
And that question brings us to the core of this paper, a framework they built called SimpleVLA-RL. It's designed specifically to apply RL to these big, complex robot models.
The secret sauce here is an algorithm called Group Relative Policy Optimization, or GRPO. Now, what's so cool about this is its simplicity. It completely sidesteps the need to create these complex, step-by-step reward functions, which, as you know, can be a total nightmare in RL. Instead, GRPO just has the robot try a task a bunch of times. And then it gives a reward to the entire sequence of actions, a thumbs up if it succeeded, a thumbs down if it failed. That's it. By just focusing on the final outcome, you get a much cleaner, more scalable way to train.
So this builds into a really elegant training loop. First, the model generates multiple attempts. The paper calls them trajectories. Next, each of those attempts gets a simple score, a 1 for success, a 0 for failure. Then, the GRPO algorithm figures out which of those attempts were actually better than the group average. And finally, the model's internal strategy, its policy, gets updated to make those successful actions more likely to happen next time. It's just a clean cycle of trial, feedback, and refinement.
Now, to really get this thing learning on its own, you needed to explore, right? To try new things. So the authors built in 3 critical enhancements. First is dynamic sampling, which just makes sure every training batch has a healthy mix of wins and losses, which keeps the learning stable. Second, they do something called clipping higher, which basically tells the learning algorithm to be more open-minded to weird, low-probability actions that surprisingly work out well. And finally, they crank up the temperature during rollout, which injects more randomness and pushes the robot to try more diverse and novel things. So, the theory is elegant, it sounds great, but does it actually work? Well, the researchers put it to the test, and they started by attacking that huge data scarcity problem head-on.
And the results are... well, they're staggering. I mean, just look at this. They took a model and trained it on just one single human demonstration for a bunch of really complex, long-term tasks. The standard imitation learning method, SFT, only managed a 17% success rate. It just couldn't learn enough from that one example. But when they added SimpleVLA-RL on top of that exact same demonstration, the success rate rocketed to almost 92%.
Yeah, let me just put that in perspective for you. That is a more than 430% improvement over the baseline. What this shows is that the model isn't just learning, it's learning incredibly efficiently. It's basically solving the task with a tiny fraction of the human data you'd normally need.
But this is where my jaw really hit the floor. RL didn't just make the model better at copying, it allowed it to discover completely new strategies. So in one task, every human demonstration showed this grasp, then move, then place motion. But the RL-trained model found a shortcut. It just learned to push the can into place. The paper calls this the pushcut phenomenon, and it's a perfect example of emergent behavior that was never, ever taught. This is the real difference between just copying and truly understanding.
This is all super impressive in a simulation, but you know the deal in robotics. The ultimate test is always the real world. Can a policy that's trained entirely in a simulation actually transfer over to a physical robot and work?
And the results here show that, yeah, it absolutely can. The team took a policy trained entirely in Sim and deployed it on a physical robot. The The standard SFT model really struggled, averaging just a 17.5% success rate, but the SimpleVLA-RL policy more than doubled that to 38.5%. And look at some of these tasks specifically. Click Bell jumps from 30% to 60%. Pick Bottle goes from a total failure at 0% all the way up to 14%. This is a huge promising sign that training with RL at a large scale in simulation is a totally viable path to building capable, real-world robots.
Okay, so let's pull all this together. What are the key takeaways for you, the practitioners out there? And just as important, what's the catch? So, for any developers watching this, here are the 4 big things to remember. First, this RL approach is a real path around that data bottleneck. Second, it leads to much better generalization, helping you avoid the overfitting that just plagues imitation learning. Third, it allows your models to discover brand new solutions, like that pushcut we talked about. And finally, it proves that this sim-to-real strategy is highly effective. But, and this is a really important but, the paper is super clear about this critical limitation. SimpleVLA-RL is not a magic wand. It absolutely needs a decent starting point. Think of it as a fine-tuner, not a from-scratch learner.
This table from the paper really says it all. If you start with a model that has a 0% success rate, RL can't do anything for you. It literally has no successful examples to learn from. The model needs to have at least a little bit of basic competence for that reinforcement learning loop to kick in and start doing its optimization magic. The better your initial model is, the more effective RL is going to be.
What this work really suggests is that this combination, a little bit of imitation to get things started, followed by a whole lot of self-exploration, might just be the path forward. And it leaves us with one final thought. If a robot can discover a pushcut all by itself today, what kind of new, even more complex skills will it discover on its own tomorrow?